2 years, there will be the transistors will double in an integrated circuit. So if we see initially, right, in this phase, probably from 1960s to 1980s, 1990s, we could see that there was this scaling. This law held very good, and we could achieve it with only physical scaling. When I say physical scaling, it means the W by L, whatever we were talking in the previous slide. So we could achieve that part in scaling the device physically itself. But later, after that point, it was little tricky. So the will Moore law continue, right? That was the kind of thing. The answer is, if you look at this evolution, right, here, it has sustained, but it has sustained with different things. So there were like some scaling constants that were introduced, and after that there was high K dielectric material used, and then EUV. So it's a amalgamation of new materials, lithographic techniques, new transistors, advanced packaging techniques. All together, the law is sustained. So that's how we look at it, that this is how the sustenance is going on. And if we look at the number of transistors, right, if we see here, right, just the monolithic integration is, we can see that in 2030, there could be, with different in monolithic, it could be greater than 200 billion. And with heterogeneous integration, we may achieve up to greater than 1 T transistors. Okay. Well, we should know also, along with Moore's law, we should know what is miniaturization. So, so if you see, right, 4 decades, there was tremendous growth, and technology scaling was one of the key driving factors. But after that, for all these PPA, this was achieved, like cost reduction per transistors, more functions, more performance, all of this was achieved. Now, what happens after 4 decades? So then came Dennard. So Dennard actually coined something called as alpha as a constant. And this constant helped in scaling everything. Like here, if you see, the voltage was scaled by alpha, oxide was scaled by alpha, W was scaled by alpha, doping was multiplied into that constant. How it helped is, see, if you see each of this table, right, everything is scaled by alpha. Now, if we ask a question here, so if we see 4 decades when it was only physical scaling, power is equal to C into B square into F. If we take that equation, we see that power was coming to 4P. If I just double put the 2x, right, it was coming to 4P, where we are probably hitting the power wall, what we call it as a power wall. So hence new techniques had to come into picture, and this voltage scaling, what did it do? Okay, let's see that. So what does this imply about power of the chip? If I double the frequency and the number of transistors every 18 years, will the chip power go up? Will the chip power stay same, or does it go down? Any thoughts? Well, if we see, the power remains constant, and that is only because of this. This is coming because of the scaling factor. We are saying its voltage is getting reduced by half, and hence that scaling factor is making a very different perspective, and power is constant with scaling. Now let's move on. So if we see, right, device scaling is backbone of our growth, and this will continue. And if we see the amount of scaling, if you see only this part of it, right? So from FinFET to GAA to complementary FET. So we'll talk about these, but this is the roadmap. You can see there's a roadmap for scaling and device evolution. So this is what something which I called as power wall. So till this point, there was a very linear transition, and linearly everything was scaling, and we could achieve the PPA, right? That's the core for which every the scaling and other things. We need that power performance area, and if we talk in today's line, it is basically the time to market, customer emission, environmental carbon emissions. So we include all these factors to achieve this. So, but after this point, there was logical cores were increasing, transistor density kept increasing, frequency remained same, power remained same. Okay. So we are in an era where we have seen this simple device to this device, where this is a Jenga pillar kind of device wherein this entire source and drain sits one above other. Sorry, the PMOS and NMOS sits one above other. So it's basically a similar device will sit one above other with a common gate which is vertical. So it's a Z direction, and this will continue. So what I want to put a fact or a thought here is that device scaling will continue, and this is the roadmap that we are kind of moving in. So if we see we saw basically we saw how the planar transistor worked, and now we slowly uh, transit our path into multi-gate transistors. So this is a typical standard cell architecture, and this is, if you see, this is the fin, and this is the fin pitch. This is CPP's contact poly pitch. This is metal pitch. And this is the height of the cell. So if we see in terms of its lithographic images, if you see the process images, this is how the planar device evolved. So from planar to stress technology, then we introduced a metal, high K metal gate. Then we had the silicon on insulator, fully depleted silicon on insulator, which is FDSY. Then we moved into FinFET, where this gate was still connected to the substrate. Then this was basically box type of FinFET, and then we had tall FinFET. And moving on, there was this GA. So this is how the things have evolved, and this is how it is evolving slowly. So if we see FinFETs and nanosheets, so this is a traditional planar, and here, if we see this gate, when you just pull it up, and we can see that a fin is built, right? So this is how a typical layout will look like. Basically, this is 4-fin device, and here we have the source, we have drain, and we have 2 fingers, and the drain is merged. And this is a single fin, 4-fin, but 1 finger. Okay. Now, what happened here? Like, how is the control of this device? See, we knew that there are, after a certain point, there's no scaling here. There were second order effects like WP and well proximity effects and short channel effects that were coming into picture for this one. So what we thought is, okay, maybe we will cover this up, get better control. And we did achieve, but the disadvantage is that there's no control or flexibility to change the width of the device. I cannot play a lot with the transistor widths. And then RC became extremely challenging because the number of capacitance that are formed are quite quite a lot of them. And then controllability of, I mean, RC, parasitic RC became a bigger challenge in FinFET. So hence there had to be something which is much better that had to come into picture. So let's go to the next one, which is basically multi-bridge channel FET, which is gate around array. So if we see here, this is where it is the wires, and if you see, these are nano wires. Both are GAA only. We call both come under GAA, but this is wires and these are nano sheets. And maybe, yeah, so I will probably take through a video. Maybe I have to, Vamshi, I may need your help here.
Yeah, please click on the share screen button again.
Yeah, and something else, right?
Yeah, prevent something else and select the window of YouTube.
Yes, okay. Okay, window and okay, maybe I'll just try this 1 second.
Razina, I guess there are few questions also. Yeah, the screen is visible. After the video, can we take
Maybe
questions
can
or
I
at the
take the
end?
question? Can I take the questions at the end if it is okay?
Yeah, please.
Oh,
Please make it full screen. The screen is visible.
Whenever semiconductor technology faced challenges, there has been a guiding light to help navigate the maze. Evolution of transistors is a major component of technology development. Planar transistors have been used for generations, with voltage scaling to save power. However, short channel effect ultimately limited usability. FinFETs were the solution and made further voltage scaling possible. Unfortunately, limitations are faced again. For ideal electrostatics, the channel needs to be fully surrounded by the gate. This is known as gate-all-around. Typical GAAs are nanowires. However, integration complexities of nanowires outweigh the benefits. This led Samsung Foundry to create a unique version of GAA with all the advantages but minimal complications. Samsung Foundry proudly introduces our multi-bridge channel FETs. MBC FETs consist of multi-stacked nanosheets. One advantage of MBC FETs is that additional area is not required to improve speed. FinFETs need fins to be laterally added, while nanosheets can be vertically stacked. MBC FETs are compatible with FinFET designs. Designers can replace FinFETs with MBC FETs without changing the footprint. Performance can also be improved without area increase. MBC FETs are the most advanced technology that provides solutions from low power to high performance applications, including AI, autonomous driving, 5G, and high performance computing. With MBC FETs, Samsung Foundry will be the guiding light for the future of the semiconductor industry. Samsung Foundry.
okay. So back to presentation. Okay, so we saw how MBC FET is giving the advantage, and in fact, this also gives the flexibility to have, like planar transistors. This also has some flexibility to with respect to the modulation of the width. Okay, so basically 1 nanosheet, 2 nanosheets, we can actually have some. There is, since it can be vertically stacked, as you saw. So the standard cell architecture, right? We can define based on it, and then we can have the flexibility. Flexibility of width is actually needed for any designer or for basically to achieve the PPA, right? Without this, it is a little bit very tricky in terms of implementation of the design, gaining the right benefits that we want, right? Okay. Of course, from the process and from the device itself, we will be getting. But from the actual design, whatever we want to achieve, I think that that flexibility is helps in bringing in differentiation. So with that, uh, the next one is buried power rail and Foxy transistors. Okay. So here what happens is our conventionally what we do is we actually have the power on top of it, on top of the other layers, what we call it as RX and other contact, and all these layers are here and the metallization is at the top. In case of buried rail technology, the power will be buried under and only the metallization for the signals will be used at the top. So this will help in uh, packaging, and it will also help with respect to IR. That's the main concern. So IR will be optimized. So if you see the next one right here, Foxy transistors. So what happens here is we have this STI, right, which is nothing but the space between the NMOS and PMOS. So this will go on reducing. So it reduces and it looks like a fork. And this is probably the next generation that will come in. Yeah, as it is said, improved version of nanosheet. With that, we'll move to the complementary FETs. This is a Z direction. And if we see here, right, we will achieve 2x density, obviously, because we are going to stack the PMOS NFET and the PFET, or mm, uh, one above the other. It's like a Jenga pillar. If we look at it, it's like a Jenga pillar kind of thing. And this will be the common gate, which will be verticals. This is how it looks like. And this is a Z directional technology mode scaling. So if you see the roadmap, right? So we saw like it from FinFET, it is evolving into gate around, all around, and nano sheets, fork sheets, and then CFETs. So with that, I think I can take a pause here before I move and take few questions if we want to take up. So Vamshi, Sajal, how do we?
Yeah. I think we have two questions. One from Girish. Girish, you can ask.
Yeah. Hi, Regila, this is Girish here. Thanks for a nice
Okay.
presentation. Yeah, this my question is regarding the multi-gate transistors. So I just wanted to understand why did the need arise for this developing a multi-gate transistors?
Okay. So see, if we look at it, the multi-gate starts from the FinFET and then slowly into gate GAA. GAA includes the MB, CFET, nanosheets, and the nanowires. The need is basically the performance, PPA. So if you want faster, you want to achieve better PPA, we will have to go for scaling. But this device scaling was not possible. See, we know the second order effects of planar technology, right? So we had LOD effects, length of diffusion. We cannot scale beyond 28. Practically, if you look at it, 28 nanometer is the last technology on, probably 22 comes into FDSOI, but 28 is something which is a pure planar technology, wherein we could, and the amount of there also, if you see, right, we still, the lithographic challenges also were coming into picture in 28 itself. Anything that we had to do, get a proper gate, we had to have a extra gate to have the like poly, I'm saying, to etch the poly properly, the needful poly properly, we had to have multiple polys, extra polys, which we called it as dummy polys. And this was needed because the etching itself of the main poly was also, so altogether, I will not say it was only one reason, it was multiple reasons. And why do we need this is because we want faster processors. You don't want the slower ones. Who is like when you go into the shop, will you choose a laptop which is, you know, a gaming laptop and which has multiple features which can do everything simultaneously? Or you want, okay, I only WhatsApp and few applications, I'm happy. So it's based on need. Again, I'm not denying that part, but I think eventually with the things evolving and with the applications that we are handling today, there's a need to move into this direction. Does that answer?
Okay, thank you. Yeah, thank you. Yeah.
The other question, should I take it at the end or?
Whatever is comfortable to you. We have 2 more
Yeah.
questions.
Okay, maybe because it's around 8:40, I will just finish in 10 minutes and then 10 minutes we can have questionnaire.
Sure.
Okay, so with that, I will just highlight, I will go into like what is standard cell library and who we are, right? So we are actually, you know, we are Lego pieces. So standard cell libraries are nothing but these are, you can imagine that Lego pieces. So we are like, these are like inverter, buffer, flip-flops, and these together. So there is a lot of tools being involved here, and finally this turns into an SOC and a proper application SOC that is built from these libraries. So these are like probably the stick diagrams of inverter NAND cells. And if you see the flow, right, we start with the specification, architecture, circuit design, then physical design, and then we do these verification checks. Then finally, we send it to the fab, and fab has its own packaging, testing, and finally, chip. So what are the subdomains? So this is specifically, again, what in Samsung we are working here on. So if you see, we have, it starts with the spec and starts with the design. So we start with transistor level design. We do the technology study. We see what has been changed, what has improved, and what are the layers that have come in. And then new circuits, innovations that are there, we try to include them. We do the robustness checks, low voltage checks, so multiple checks are being performed. And then we have a layout team who will do all these, who will implement this design into the layers and make it into the form that it can be sent to the fab. And we have characterization, wherein each of these cell has to be cell, or each of the Lego piece actually has to be put into a particular format of file which is usable by the SOCs. So we have to model the timing for different loads and different slew conditions. So initially, if you look at it, right, when it was 130 nanometer, even much beyond, or even till probably 90 nanometer, 40 nanometer, we could just give the power tables and timings and we could stay with that. But as we evolved, we had to, as the technology evolved, there were more challenges. So we had to give the capacitance information, Miller capacitance information, noise information into a Liberty file. As we moved further down, we had to again give variation also into picture. well, I have not captured the local layout effect, which is LLE, which is in 2 nanometer technology, where we it's like a small, if you have a small house beside a tall building, the shadow of the tall building falling on the small house, it's like vitamin D effect, right? So it's like kind of that kind of scenario has to be captured in characterization. So it's basically LLE modeling is what we call, and it's majorly done in 2 nanometer and further technologies. And we also have a benchmarking team, and we do the uh, so whenever we develop a library, right, we have to see what is the performance, what is the PPA benefit that we are getting with whatever is existing in the market or whatever is existing in the previous node, whatever is existing across, right? So we have to do a benchmarking, and this team actually works on those, and it also defines, based on these results, it also defines the architecture. It defines like, okay, this is how the we have to change these routings, these pin access, this is better. So these kind of, all these are the activities that Standard Cell library team and Samsung India is working on. Okay, so this is just a simple example of how a planar layout or architecture looks like. So we call it as 8-track standard cell library. Why do we call 8-track? Is because we have um, the number of power rails and pin access that we can get. Based on that, the tracks are defined. Coming to FinFET, there are more layers. Here we define it, we no more define it based on the routings. It's height and the fin. So based on that, we have a calculation factor, and based on that, we actually define the architecture of the library or height of the cell, or we call it as so it's no more like defined 8-track, and because it's a multiple of the fin also in these cases. And if you see the layers that have increased, right, just this is a very basic stick diagram, but honestly speaking, you can say almost like 3x 4x amount of layers have been added in a when we move from planar to FinFET. Well, in some other talk, I will probably in future, I will also briefly share how the amalgamation of these two can also bring a new process technology node, which is actually a 17 nanometer node. So maybe we'll talk about it some other time. So this is the flow that we follow. We get the spec from customer. We do the architecture setups. We do the cell design, layout verification. We also do the behavioral models, set up the characterization, get the decay, and this complete decay is then we actually share to the customer. So right from spec to customers, and in fact with customer also there are interactions where based on the application we discuss what would be the best library that they can use, or we give a portfolio of libraries saying these are the things are available, this, and if there are specific specifications we actually modulate, and sometimes we do develop the new library. Okay. Well, with that, I'll move to the next. Very lightly I will touch upon because in the era of AI, if we don't talk about, at least if we don't touch base and say what's happening on this side, I think I'll not do justice. So if in my words, if I have to say how it applies in this domain, I will say embrace, evolve, and apply. So first thing is, whatever are the things that are coming on AI, important is we embrace it, then we evolve around, see what is in there, and then eventually apply. So if we see in Foundry, as a Foundry, AI will be used in terms of in chiplets, in process steps, integration, multiple places we can use. If we break down the same into standard cell, right? Many of the EDA tool vendors like Synopsys, Cadence are already using few of the algorithms. ML is quite available. It was available earlier also. ML is predictable algorithms. But again, AI also is being how well AI can itself tell us that, okay, this is what is your numbers for this library. So the things are evolving there. Optimizations on layout on that front also, area on that front also, there are AI is evolving, and of course chiplets and wafer package levels also. There is work that is happening, but I will say like this is happening, evolving. We have to embrace it, but the core will stay. The core basics have to be there in order that we apply this. Without the core and just having AI, I think it will not bridge the gap. So both need to go hand in hand. The entire ecosystem needs to go hand in hand in order that we make a better um, time. I mean, PAT is improved, or we bring in efficiency, we bring in more productivity. So for all of that, everything has to move hand in hand. But core has to stay. Core. There is still a very different value, what I can say, for the core basics. Okay, so I think, so with that, will the journey continue? And will this evolution continue? Yes, it will. As we saw, there are many other transistors which are evolving, coming in, and yeah, it will continue. And if we see the roadmap, we also see SF2A, SF2Z, SF2P, 1.4. There's research going on, and these are already in market. So I think the story is on. But how the story will sustain or move is also like it's innovations in design, evolving EDA and materials, lithography, all will go hand in hand to sustain the uh, evolution. So I think with that, I open the floor for Q&A. And thank you very much for hearing me out. And thank you, Sajal, Vamshi, giving me this opportunity to present here in IEEE SEDA. Thank you very much.
Guys, you can speak up. I mean, you can access the mic and please ask your questions. And also, questions in the chat box and also.
Yeah. So, Vamsi, better you can moderate, else it will be very confusing. Let's go.
Yeah, sure.
Let's start with Vimla ma'am, then Venugopal sir, then chat box. Okay.
Sure. Vimla ma'am, please.
Yes, thank you. Hi, Regina. Thank you for this nice presentation. I'm very happy to see that an industry person is talking to the core of transistors. So, since I'm working more into transistor, happy to connect with you. And thank you, Sajal, for making such person or to the talk. So, just I want to clarify about the SOI technology. I think you have not touched anything about that. So
Yeah.
I have worked more into that. So just I want to know like the current technology what they are using, maybe the FinFET technology or gate all-around technology or whatever you are talking about the future 4 technology or other thing. Whether they are using with SOI technology or with the traditional planar technology only they were using.
Okay, so it's based on the application is what I will call it out, because SOI has better in terms of power and leakage, it is better because of the insulation that it is having. But however, having said that, the number of masks increases, and probably when you see which, so that's the decision many times customers take. whether they want. But yeah, I mean, I think some informations are confidential. Maybe I cannot share whether we are doing it in Samsung. Do we have customers in Samsung? I can talk about it, but the reality is it's based on application. If you see a smart card, right? I mean, smart card is something like 16 nanometer, 90 nanometer technology also can go in a smart card. So it's based on the application where the customer wants and what they want to use.
Okay. Since most of the research paper, what we are referring is completely in SOI based technology. We are not using any traditional structure what we are having. So just I have, since you are not touched that portion, just I have a clarification on it. So that's it. So and one more thing is, maybe you have discussed about this AI can be used in the transistor level 3 nanometer, 5 nanometer. Can you please elaborate little bit how are in which portion can be used in the transistor level design AI?
Okay, so if you see, right, so you might be doing some of the routines again and again. For example, I'll say low voltage check. You want to see how the transistor will go, how low it can go, right? For a particular voltage, how it is going. So if we want to actually check that kind of thing, these are the things which we can actually uh, probably more and more as data gets into it, we can actually store that data and make it predictive,
Okay.
right?
Maybe the like, yeah, I'm not able to hear your voice properly. Some lag is there.
Sajal, maybe
No,
you
it's
want
clear
to.
from my end.
Actually, a noise is coming from Vimla ma'am side. Vimla ma'am, maybe you can connect with Rajila ma'am later outside.
Yes. Okay. Thank you, ma'am. Thank you so much.
Thank you.
Venugopal sir, please go ahead.
Yeah, good evening, Rachila ma'am. It was a very good and nice presentation today, which and welcome for the good initiative from Sajal sir and Vamshi and from SEDA, the first session. And my just a question is again a little bit related to Imla ma'am also that whatever that you said complementary FETs, CFETs and other thing. Is it based on the technology, why it is 1 nanometer or 2 nanometer? Based on that, we are going to select those transistors, no? But is it how it will be going to be different from the? Is it a latest one? Which is the latest transistors we can say? Is it a complementary FETs or you said they're all GAAs only? They're all GAAs. Many of
Right.
the
So,
GAAs were there. Is on what
yeah.
basis will we?
Yeah, so let me answer. So if you see the 2 nanometer technology, it is based on MBCFET,
Okay.
the nanosheet. Okay. So the whatever fork sheets, buried rail is one type of, I can say it's a kind of packaging and it's a kind of, it comes in that category. But fork sheet again is next evolution. CFET, which we talked about, is the next evolution. So even I don't know what will be the nanometer or what will be the exact thing where it will be implemented. So currently 2 nanometer, whatever we are working, it's all MB CFET, and I think you saw it in the video as well.
Yes, madam. Thank you. Thank you for the inputs and thank you, sir. Thank you once again.
Thank you, sir. Saptarishi, please.
Hello. Thank you, Rajula ma'am, for the very well structured PPT today. So my question is basically from one of your last slides about the standard cell development mostly. So
Yeah.
usually like during the standard cell development phase, like after the design, the layout team takes over the design and after that the characterization happens. So it's sort of like, I think it's a iterative process, right? So as you said that it's like you're using some sort of AI also. So are you using some sort of AI to basically reduce that iterations, the number of iterations? Because when we go from schematic to the layout and eventually the post layout simulations, the specs might not always match.
Yeah, very, very good question, because This question is actually not in terms of only the technology or the thing. I would rather say it is also the people part of it here. So to avoid the iterations, right? All it takes is actually you go and see how the design is working out, or the designer goes into the layout and sees how the layout is being drawn. So today, if we talk about, again, coming to so this was one point which probably even I forgot highlighting. I said evolving, it's a cohesion of all the materials and all. But in standard cell domain, if you see, right, the domains are merging. Everyone needs to know everything, honestly speaking. Should know design, you should know characterization, you should know layout, you should know benchmarking, probably you should know all of these to make a good call, take the right decisions. Because if you allow the designer to work in silos, right, I think they will not get what, and you will only end up in iterations. So if you work, when the designer works with the layout, and at the same time, the characterization team also pitches in and takes the early, because in the current scenario, it's not just about the technology, right? It's also the new custom designs that we give. It's all like custom. Like, see, everything is custom today. The tiffin dabba that is coming is customized. You have custom passports that are coming in. Why not custom libraries with custom applications that need? So every design, and in this case, all of them have to work hands in hand. Because if it's a new design, if characterization gets in the last phase, right, I think we cannot meet the timelines itself. So it's all merging. And again, on the second part of your question, where AI can help, it will help in the cycle times itself. So for example, you drew a layout. Now, once you have drawn a layout, you know that it is not the optimized one. So you will feed it saying this is not optimized, or you will have tools which will tell you this is the best placement. A flip-flop can be done in 10 different ways. What is your best placement? You can always use AI algorithms. See, AI is a big word, but ideally, I will think it more like automation, which is made more predictive, more where you can bring in more differentiation. So you predict it, and that's what. Characterization, simulation, the moment you have a PDK, you know which PDK was previously. And in fact, TDA tool vendors are actually coming and pushing for us. But on this front, you can get the PDK PPA, basically based on just the PDK change, technology change. What is my PPA for the new library, for this library which I have to recharacterize? So these are the things where you can predict it. You don't have to really do a actual characterization, do the compare. You don't have to do that. You just pass all the inputs, predict, get the result.
Yeah,
Thank you. Okay. So, Vamsi, I think it's already 9. I think we have 3 pre-submitted questions from Apratim.
So
Apratim, Renju ma'am, and Krishnan. I think we'll take 3 questions. After that, maybe we can close. And I would request Vimla ma'am and I think Param Shivam. I think maybe you can connect with Rajila over LinkedIn. And you can send us the question, redirect to Rajila and get the answer. But let's take Apratim, Renuka, and Krishnan question, and then we can close. I don't want like people in the same. Okay?
Sure.
Please.
The question from Renuka ma'am: how do you perform age testing and PPA comparison?
Okay, aging, we do have aging models. So basically, we use those models and do some iterations of simulations. And based on that, honestly speaking, if it fails, we do have to go back to the process guys. We have to check with them whether it's allowed or not. And then we decide whether we can go with it or not. The second part of the question, how it impacts the PPA? Is that
No.
the question?
Only the question is, how do you perform age testing and PPA comparison?
Okay, PPA, okay, age testing, this is how we do. PPA, we do through the benchmarking. So you actually do the PNR. You take a set of cells, you actually take it through STA, you sign it off, and then you see what is its power in real time design. So we do have sample design like ARM processor designs, Cortex designs we have. So we pass it through the real design and see how the library is performing.
I hope, Renuka ma'am, this answered your question. And the next question is from Gobal Krishnanan. Which simulation tool using to design Sinatra's GTS, NDS, Quantum ATK, Silvaco?
Oh, sorry.
Which simulation tool used to design Centaurus,
Okay.
Which simulation tool? Maybe
GTS?
I'll take one. Ma'am, which simulation tool you are using for simulation, basically?
Simulation for the characterization and putting it in the model, or
What,
at design level, what is
what
the
design?
design normal? I think tool wise, I don't remember, but I think we have internal tools also, but we use spice simulations, basic spice simulations.
Just to answer Krishnan, basically the industry standard tool is like Spice tool. You can take any cadence and synopsis tool, and for designing, you can take any cadence virtuoso. Generally, this is the industry standard, but there are some limitations due to which Regula ma'am may not take the exact name. Okay.
Yes.
And maybe the follow-up question on that: how to resolve the leakage analysis in tunneling using AI?
Oh, okay. Sorry. Probably we have not gone this far, but very good question, I can say. And if there's something research and anything help needed, maybe we can also understand with you.
Yeah. Okay. Thank you, ma'am. I think
Maybe
Vamsi can take last question from Apratim.
Yes, there is a one generic question from Apratim. I would like to ask a question on behalf of students. With so much advancement in tech nodes, how can a student learn about this and also prepare for joining standard cell library engineering job out of college?
Okay. RC basics, I will say. So with job, I think with job you will anyways learn. But in current scenario, what we are seeing is it's, I will not say it is the uh, whatever the actual thing. The thing is, what is happening is because there are multiple things. There's AI to learn, this to learn, that to learn. So I think there is a lot of diffusion. It's like this that is happening in the learning cycle. So first is RC basics have to be good and understand what the circuit is actually doing. And many times you may feel like, okay, I have done 2 years, 1 year, I'm good. I have understood everything. Or you have run few simulations, you suddenly feel, yeah, it's all I know everything. But honestly, it takes much longer. And whatever today I've shared probably is my also part of 20. I didn't start with vacuum tube though. I started with MOSFET, but the journey, and the team is doing 2 nanometer nodes here. So it has taken years for us also to understand and evolve. So anything of this thing will take, it's an experience that you will evolve, but basics, don't leave your basics. Preparation. So questions will be mostly on the basics. We also know what is academia syllabus, and we don't go and yeah, but in general, what is there in internet? I think explore that, understand that. This is a YouTube video. Today, whatever I've presented is everything from internet. It's all there available. So I think it's about exploring.
Apratim raised. Sorry.
Acha.
Apratim, do you want to add
Yeah,
something?
yeah. Thank you, ma'am, for that. Actually, I was seeing a lot of questions about AI, and AI is a buzzword now, and everyone is talking about it. And I just wanted you, like you told, you started with 180 nanometer, today 2 nanometer. I think the basics are the same, the fundamentals are the same. I think I just wanted to highlight that to the students that we should
Maybe,
not be the
yeah.
site of the
See,
real code engineering. Yeah. Thank you, ma'am, for touching it up.
the best example is, coconut. The green outer shell is also coconut. You layer it out, remove the brown is also coconut. Then you cut it. The white shell, the white essence that we have is also coconut. So finally, it is what is the core, right? How much of AI? So that's why I said it's an application. You have a tool to do something about it. But basically, you can cut the coconut with tools, you can grate the coconut with the tools, but you cannot make the coconut. I mean, that actual essence still remains the same. So the base core remains the same. So I think focus on the core, have good automation skills. I think you will evolve. That's my probably one tip to academia. Yeah.
Thank you, ma'am. I think.
Okay. Thank you. Okay, thank you all. Oh, thank you. Okay.
Vamsi, you're on mute.
Yeah, Sajal, so the stage is yours. Ma'am, thank you again.
Okay, so yeah, thank you, ma'am, for giving this presentation. I think it's very good to see we have 10 minutes above our scheduled time, and I can see 48 participants out of 54, which directly tells us this event is like this lecture is very good. And I myself learned about a lot of foods today, complementary fat, pork, etc. But definitely I'll catch you and learn more about. And I would appreciate everyone if you want to learn more about CFETs and all other new technology nodes, please provide the feedback in the feedback form, and I'll try to convince Regila ma'am again to talk in deep for those FETs. It's very difficult to get it, but yeah, I'll talk to her and we'll see what we can learn. Okay.
Yeah,
So
I should.
again,
Yeah, Sajal, finish. Maybe I'll.
yeah. I think again I would like to thank you. I think thank you for accepting this invitation with the bad throat. I know it's little difficult. You are struggling in between, but yeah, overall it's very engaging and thank you.
Okay. Yeah. So again, on the material side, I would also thank my colleagues, Mitesh and Utkarsh, who have actually Mitesh is doing PhD on material science. So maybe we can see if we want to invite him as a guest also sometime. So I think they have done a lot of, they helped me on in many of these things, and truly thank you for this opportunity. Yeah.
Yeah. Thank you, ma'am, for your nice talk. Guys, the feedback form has been shared in the chat box, and also if you can scan the QR code and please fill the feedback form. Once the participant fill the feedback form, and when we verify their membership, if they should have the SEDA membership, then they will receive the certificate. And one of the surprise is like few of the selected participants, like it's like we thought of to give the free access for the SEDA flagship event. The selected participants will get an email, and with the future event details, if they are interested, they can participate it. Sajal sir, anything to add?
Yeah, just to add, guys, it's very important to fill the feedback because it will give us the feedback for the future events. Also, you may get a chance to get free pass for the upcoming flagship event from SEDA. So whatever I mentioned, like surprise, this is the surprise. You will get a fully paid pass for the flagship event. So please ensure you will give feedback. You can fill feedback, and that is kind of entry for that kind of a lucky draw. Okay. So maybe we'll hold this screen for maybe 30 seconds, Vamsi, and then we can take group
Sir,
feedback.
already the link has been shared in the chat box, sir.
Okay.
They can
Okay.
fill it. And I request
Okay.
everyone to switch on the cam so I can take one final group pic.
But Vamsi, I think after this call they cannot, right? So maybe send the link or QR code to all the participants later.
Sure, sir, I will do it.
Okay.
I'll just cross-verify who has attended and will shoot an email with the
Yes.
feedback.
Yes.
I request
Okay.
everyone to switch on your cameras so I can take a nice group pic.
Guys, don't feel shy. Please turn on the cameras. I know it's a Saturday evening, so it's okay. Only 4. Vimla ma'am. Okay. Raj. How we can fit everyone, Vamsi, in one screen?
Sir, it's I just did a few settings in my side, so I can only see who are switching on the video.
Yeah, but you can fit everyone who switch on the video.
Yeah, yes, sir, we can.
I'm not expert in this kind of video. Okay. Anyone else is coming?
Yes, sir. I guess most of them did. Guys, on a count of 3, 2, 1, please give a smile. 3, 2, 1. Yeah, I'll just take one more. Okay. On a count of 3, 2, 1, please. Okay. Yeah. Thank you so much. Guys, please don't forget to fill the feedback form, and please follow our social media handles. There will be much more updates and much more webinars and workshops soon. Thank you all for joining again. Yeah.
Just one more, Vamsi. Just an announcement, guys, to all the new participants, like Exicom members are aware. We are doing a lot of events on open source tools. I think Krishnan already asked that question. So today only we have finalized 2 events on open source tool. You will see the notification soon. And please ensure you will register. There is very nominal fees, and will ensure like you will see a lot of events in coming future for students on open source tool. We'll make sure by end of the year you will up and running and you will know what you need to do with open source tools and how to leverage it. I think you will see the notification soon. So as Vamsi mentioned, please follow all those social media handle, LinkedIn, Instagram. Not sure what else we have, but yeah, I think we are uploading this on YouTube, Vamsi.
Yes, yes, sir, we will.
Good. So you can follow our YouTube channel as well. So yeah, I think thanks again and see you soon next month.
Bye, everyone.
Okay.
Thank you.
Thank you. Good night.
Thank you, guys. Bye, everyone.
Bye.